Hello, welcome to Stats Lab. We're going to play around with distributions today and a new set of numbers. Let's check it out online. So here we have our assignment, week 3, measures of spread and center, and there's a lab description and data. There's also a link to the data in the description. In the description here, we're going to be playing around with birth rates. Data on this was collected over many years in Philadelphia at hospitals, and we have the birth weight in grams of a bunch of babies, newborns. The spreadsheet will come to you in shared view only, so you'll have to either download it as an Excel sheet or make a copy of it so you can play with it in Sheets. So I'm going to choose to make a copy and play with it in Sheets. And give it a better name, file it somewhere. Appropriate so you can find it later. And I can get rid of the original now. So this is the data, it's weight in grams. There's some information about where I got it from here, who collected the data, at least one of the people. And what we're going to do is, instead of playing with the original data set, we're going to take a random sample of 100 of those birth weights. So there's over 1,000 birth weights collected in the sample. We're just going to grab 100 of them to play with. So your random sample tab down here will have a slightly different set of numbers than me, but there will be 100 of them. Now, one problem with the random selection tools in Excel and Google and other spreadsheets is that every time you do something, it re-randomizes, reselects that random data. So we're going to have to override that. So first, we'll just take a look at the description here, what we're going to do. So what we're going to do here is compare and contrast empirical data with a theoretical distribution. The theoretical distribution I've mentioned before is what's called a normal distribution. So we're going to take a look at, does this sample data seem to be normally distributed? And then we could ask ourselves, based on some other information about why or why not it might be. As far as rounding here, the data was collected in grams, and so we'll take that to 1 decimal place beyond the whole number of grams that was recorded. Definitely have to have this birth weight spreadsheet that I've started. And you could either make your own simple random sample from that using a random generator to pick 100 birth weights, or you can check out my sheet 2, which I was just showing you, and go with that. And then I have those in a separate sheet. So once we lock down our random selection, so it doesn't keep re-randomizing, we will start making some histograms and calculating sampling statistics and then describe what we see. So let's get busy. The things we'll calculate are the standard statistics we've been playing with, the mean, the standard deviation, the count, the 5-number summary, amending that to include range, interquartile range, and a couple of other things. So first thing I want to do is I want to stop this from randomizing. It's got a ran between option there. So to do that, I'm going to select that 100. And I'm going to copy it. And I'm going to paste it back on top of itself in a way that's going to replace the random selection with these actual numbers. Instead of being a formula in each spot, I'm going to turn it to numbers. To do that, once I've copied it, I'm going to go to Edit, Paste Special, and just paste the values back. And so now, instead of a formula saying, hey, go grab a random number from the list over here, it now says, oh, we just got this number right here. So that step's going to be important. Otherwise, your numbers, your calculations, and your histogram will keep shifting on you every time you do something. And that's kind of annoying. So I have my random sample of 100, and now I'm going to start playing with it. So I like to do my summary statistics before I start doing anything else. So I'm just going to make a new column over here called statistics and start putting my standard things in there. Like I usually want to know the count, the sample size, that's n. And although I know it here, it's something you want to make sure you list. Let's see, what else do we want? We want the mean. We want the standard deviation. We want we could throw the coefficient of variation in here for fun, although I don't ask for it. But we do want, I'll leave a little space here, the min, Q1, and so on. Median, Q3, and the max. Based on the 5-number summary, I want some other statistics, like I can calculate the range of data, the interquartile range. We've used the interquartile range and the quartiles to calculate these fences that we believe usual data should be in and unusual data should be outside of. So I'm going to put a place here for my low fence and my high fence, or upper fence, whatever you want to call it, and start building some formulas. So I want to use the count command. And in this case, there's nothing else in that column but the title. Count only counts numbers. And so in column A, it says there are 100 numbers. So that's good to confirm. I want the average. Again, most of these commands, we can select the whole column, even though there's a lot more cells. And standard deviation, we're going to use stdev for that, which is sample standard deviation. Coefficient of variation, remember, is the standard deviation with respect to the mean as a percentage. So I'm going to reformat that as a percent, and 1 decimal point is good. And each of these, I really only need 1 decimal point of accuracy. Your minimum, oops, I forgot my equals. So just do your calculations. Feel free to fast forward through this part. So we'll draw a box plot in a little bit. And those look good. Range, so is the distance from the max to the min. Interquartile range is the distance from the first quartile to the third quartile. High fence, remember, is we expand that interquartile range, take that expansion away from the first quartile, add it to the third quartile. We'll draw this out in a minute. So that would be equal to Q1 minus 150%, or 1.5 times the interquartile range. And my high fence would be Q3 plus 150%, or 1.5 times that interquartile range. So according to the 5-number summary and that interquartile range, usual values for birth weight, according to this sample, should be between about 2,000 and 4,500. So sometimes I like to sort my data. And a trick for highlighting on a spreadsheet is if you start at the top or the bottom, say I'm starting at the top, and on a Windows type computer, it's a Control-Shift down arrow. We'll look for the bottom of the list. On a Mac, it would be Command-Shift down arrow. Gets the whole list there. And then I want to go to data, sort the range. Note it does have a header column or header row, and then I want to sort by that birth weight. So I can kind of look at it and notice there's a couple of numbers above 4,500-ish, and at the top there, let's see, 2,000 was my lower fence. There are a few numbers below 2,000. So according to that extended interquartile range, that low fence and the high fence, there are a few values unusually high and unusually low in this birth weight data. That's one way to talk about the outliers or possible outliers. Let's see, let's just clean this up a little bit. All right, so next I want to take my data and make some box plots. Not box plots, histograms. Box plot will draw on top of a histogram. So let's see, it picked a line chart. I would like a histogram. And let me just zoom out. So it chose to scale by 400. Hey, that looks pretty good. I like that. All right, so I'm going to go with that one. I'm going to make another one just for comparison. So I'm just going to shrink this down a little and move it over. All right, let's try again. And usually I have to make a few of them and then decide if any is better than the others or if they're all about the same. And histogram again. This time I'm going to take control of the information down there And usually Google works pretty well for me, Google Sheets, but every once in a while it doesn't let me customize the things the way I like. And the same thing with Excel. Sometimes it works great for me, sometimes it doesn't do what I wanted. Let's say they have a bucket size automatically chosen of 400 for this data. Yours may not work the same way because you have a different sample set than I do, right? We're sampling randomly 100 of those 1,100 birth weights. So you might get a different grouping down here. So instead of auto, so my data goes from 1,000-ish up to 5,000 roughly. So I'm going to try picking a nicer number than 400, and I'm going to try scaling by 500. So I'm just going to click on auto and type 500, hit enter, and that's by 500. Now it started at 1,000. Maybe you want to start at a different place. You can often tell Google to do that by picking a different minimum for the horizontal axis. And maybe I want to try, what if I start at 500? Enter, and it should redraw that. So here I can see, well, apparently Google picked better than me. There wasn't a point of starting at 500. But sometimes we do like to pick our starting point. Like I could start at 100, and it's going to look pretty different. I could have started at 300. All right. And again, because this is an app running in a browser, it works best in Chrome. So if you're running it in Edge or Safari or Firefox, it might not behave exactly the same way. And my apologies, that's just the internet these days. All right, I'm just going to go back with what it gave me and say I like this. And whoop, let's resize it and stick it next to the other for comparison. So these are my two different ones here. Get rid of the editor and just expand this a little bit. All right, so yeah, they're both good histograms. Maybe tomorrow I'll like this one better, but I'm going to go with the 500 one instead. And so the next thing I want to do is I want to draw this out on paper. So I did this earlier. I just want to show you what my sketch looks like. I had a slightly different random sample, so it's going to look a little different, but I'll just show you my by hand sketch. Take a picture of it with my phone and send it to myself. Here we go. So here's a picture, to the best of my artistic ability, of a different random sample of birth weights. So here I have my scale by 500, 1,000, 1,500, 2,000, 2,500, 3,000. I only labeled the 1,000 ones. If you wanted to label every single mark, that's fine too. To get the column heights, what I had to do was just look at the one Google gave me. If I click on it and then point to the columns, it'll say, hey, there's a count of 2 in that column. There's a count of 1 in that column, 8, 15, 33, 35, and so on. So you can get those counts from there. So I'm skipping over making a frequency table, which is fine in this application. I don't really care to have a frequency table. I just want to see a picture of the distribution. What does that mean? It means, well, how are the numbers laid out? Where are they spread thinly? Where are they clumped densely? So how would I describe this? Well, this one right here appears to have a left skew. There's more of a tail on the left side, but there is some clumping over here. And if you note my mean, blow that up a little bit, is almost 3,300. And so I can see the clumping happens around 3,300 there and 3,300 here. So my mean is in this stack. There's the median. The median is 3,400, which is just on the edge of this taller stack there. And mean and the median are both in this stack right here. Could I say this is the mode? Well, it's definitely the largest group, but usually mode means most frequently occurring individual element. Let's see, my little fence has too many decimals. Clean that sucker up. And then I'm going to send both of these charts to a new tab. So let's see, move to own sheet. And again, for this one, move to own sheet. Okay, so now I have a little more room here to work. All right, so what else should we take a look at? So we constructed a couple of histograms. I'm in the 6 to 15 intervals, and then I sketched my favorite one. So like I showed here, you're going to have to make a sketch. If you can draw straight lines without a ruler, cool. If you need a ruler, grab it. I've also included here a sketch on top of my box plot. These stars are my fences. So the first time I did this, I had a slightly different set of numbers. And so here, my upper fence is beyond the maximum. So in this data set, there were no unusually high birth weights. But you can see that here is the lower fence, that star. So there are some values, at least the minimum, that is unusually low compared to the majority of data. And so if we look down from that star falls in this group right here. So I have 1, 2 birth weights that were unusually low compared to the extended box plot, lower fence. I also marked on here my standard deviations. Remember, standard deviation is an average measure of spread from the mean. So from the mean, I add 1 standard deviation to the right. From the mean, I add 2 standard deviations, and then 3 standard deviations. And then I just made an estimate about where those marks are on here. Going the other way, there's 1 standard deviation to the left. I made a mark, 2 to the left, and 3 to the left. So I'm going to calculate those numbers right now. So I need a new group over here. I'm going to call this group standard deviations. Standard deviations. And I'm going to have 2 columns for standard deviation. I'm going to mark the z-score, how many standard deviations I am from the mean, and then the actual weight that goes with that, which I have to calculate based on the mean and the standard deviation. So usually we graph the -3rd, -2nd, -1st. 0 is the mean. 1, 2, 3 standard deviations from the mean. To calculate these, what I just need to do is take the mean and look 3 standard deviations to the left. So formula-wise, that looks like this, equals find your mean, right there. And then I'm going to add a -3 times standard deviation. And there's my standard deviation, and then hit enter. Now, what I'd like to do is fill this down, but the problem with filling it down is it will change this cell reference when I copy it down 1 to that cell reference, and that's cool because I do want it to look -2 next. Unfortunately, it'll take this mean and look below for it, and it'll take this standard deviation and look below. Anytime you copy a formula down, it wants to shift the cell reference down with it. So to fix that, what I have to do is say, don't mess with my mean, don't mess with my standard deviation. To fix them, we just put a $sign in front. So I'm going to go $sign, and yours may be in a different spot. So $sign letter, $sign number to fix the mean. The purple number is my standard deviation count. The blue number here is my actual standard deviation value above. And so I want to $sign that and $sign that. So this says don't mess with the standard deviation, don't mess with the mean, but please shift the number we're using to count standard deviations. So hit enter, then click back on the bottom corner and fill that down. And I should get the numbers representing what it means to be 1 standard deviation below average and 1 standard deviation above average. So I'll compare that to my histogram. So this is about 2,700 would be the weight that would be 1 standard deviation below. And almost 4,000 is 1 standard deviation above. So about 27 to 39. And let's look at these charts. 27 is about here-ish. And 39 is over here. And we can see the majority of data, 1, 2, 3, almost 4 columns, live within 1 standard deviation. And that's what we're going to find usually. Most of the data, at least 50%, is within. Is that always going to happen? No. You could have a U-shaped data where there's almost nothing in the middle and everything's out on the edges stacked up really high. We looked at one of those in class recently. So you never know what can happen. All right, so I have those counts there. So what I'm going to do with those counts next, let's see where they go, is I want to go mark off each of these numbers, roughly where they live, on my hand-drawn histogram. So you're going to make a mark where you believe, according to the scale you drew for the histogram, where the mean X bar is, where the 1 standard deviation below was, 2 standard deviations below, and 3 standard deviations below. So you're going to make those marks there. And then shortly what we're going to do is we're going to count how many elements, how many data points, in this case weights, live between these 2 numbers. Now I'm going to use the computer to help me count those. Let's take a look at where we are here. So we've constructed our histograms, number 1 in the data collection part. We've calculated X bar, S, and a whole bunch of other stuff for the second part. So you need to write some descriptions about what your data looks like. So for example, again, if I look back at mine and I take a look at either histogram, I could say the data seems to be skewed left with a few, very few birth weights that were low maybe I could be even more specific. There were very few birth weights below 2,600 kilograms. So that defines the skew left. Most of the data was clumped around the median, which was about 3,400 grams for the birth weight. And in this case, I did have a slight tail on the end. There were a couple of birth weights in above 4,200 grams, but most of the babies seemed to be within 3,000 and 4,000 grams when they were born. Okay, so again, some kind of verbal description of what this picture looks like, and throw a few numbers in there for reference. Moving along, then on another piece of paper, you're going to write down some answers. Don't forget to draw your box plot above. Box plot. B's and P's look the same to me. They're just rotated. So the IRQ goes from blank to blank. What does that mean? Well, if we look at our data, the IRQ goes from about 3,000 to about 3,000 to about 3,600 grams. Just what is the starting and ending value of your box in the box plot? How big is the IQR? So I calculated the RQR here. My RQR was about 600 grams wide. 16th percentile and 84th percentile, we need to calculate those. We have the median, and then we're going to do some percentile rank based on the number of 3,000 grams and see what happens. And these will be different. So I need to, we need to do some work to answer questions 7, 8, and 9. We have already done the upper and lower fences and identified the outliers. We just need to write that down somewhere. So either in your spreadsheet, you're going to type up your answer. Hey, yeah, there are some outliers. I found these two numbers were below and this number was above. Maybe you found no upper outliers. Everyone's probably going to find lower outliers, and we'll talk about why. So let's see, where am I? Oh, 4 and 5 also. 16th percentile. So coming back down here, let's do a little more work. Percentiles, and I want P16, and so that would just be found using the percentile command, and I want just regular percentile, and it says where's your data, comma, which percentile do you want as a decimal? So that would be 0.16, 16 hundredths, 16%, close, enter. And the computer tells me that that's about 2,700-ish. I have more decimals than I needed. P84. And same idea, percentile. Oops, not permute, percentile. And it's grabbing the same thing as before. Sometimes Google will guess, hey, you want to do the same thing again or something similar? I want the 84th percentile, enter. So that's about 3,800 grams. What does it mean to be the 84th percentile? Well, according to this sample, 84% of newborn babies were at or below 3,800 grams when they were born. That's what this tells me. 16%, which would be above 84, coincidence I picked 16 there, sort of, would be above 3,800 grams. That's what that tells me. So write a statement about what that means. Next, we need to do a percentile rank. So in that case, what we want to do is we already know that we want to know how many babies are, let me look at it again. It said, what percent of the weights are at most 3,000 grams? So that's, again, what's the percentile that goes with 3,000 grams? At most means up to. So 3,000 is the answer. I want to know what percent goes with that. So I'm going to do this backwards because I know what the weight is. I need to know what percentile it is. And that's called percentile rank on the spreadsheet. So where does the mass of 3,000 grams sit in this list, roughly? So percentile rank this time, highlight the data, comma, 3,000 is the data value I'm curious about, and the computer will spit back to me a percentage. Rewrite that as a percent. So it looks like it's about the 25th, 26th percentile. So what does that mean? 25, 26% of newborn babies have a mass of 3,000 grams or less, is what that tells me right there. Now, I'm also asked another question, and that was what weights are more than 3,000? What percent of weights are more than? Well, this is the percent of weights less than, so I just want 100% minus that. So for this one, I'm just going to go equals 1 minus. Why 1? Because in the background, spreadsheets treat percentages as decimals. 100% is 1 as a decimal. So 100% minus that. So according to this, about 74% of babies have a birth weight or a birth mass that is 3,000 or more. That's what this tells me here. All right, we're flying along here. Moving on, we did this part here, calculate 1 standard deviation on each side of the mean, then 2, and then 3. Next, we need to figure out what percent of the data falls within those. So now I have some counting to do with the spreadsheet. This part's a little bit tricky. So I'm going to put another column here. I'm just going to call that count for now, for lack of a better name. And I want to count, for example, how many of the numbers were less than this value right here. Okay, and that's going to help me figure out how many are between. So to do that, I'm going to use the COUNTIF command. And at the end of this, I offer some spreadsheet tips. If you want to count the numbers in a list that are less than 2,000, you would enter something like this. Equals COUNTIF, pick your range of data you want to look at, comma, quotes are important. And then we want to compare each of these numbers to this statement right here. So it's going to check one at a time. Is this number less than 2,000? Is the next number less than 2,000? And so on. It's going to count the ones that are. So, and we'll do that by hand first, and then we'll do it with the computer. So let's see, did I sort these? I did. All right. So my first standard deviation was about 3,900. So I'm just going to scroll through the list looking for stuff that's close to 3,900. All right, so that's too big, that's just right. So if I highlight all of those numbers, the computer will tell me how many numbers I highlighted by going down to the summary in the bottom right and saying, hey, count, how many did you find? The computer found 91 of them, okay? So 91 out of 100 numbers were less than 1 standard deviation. I need to go between the first standard deviation and on each side, so I get a little more work to do. So let's check that. We're going to try that COUNTIF. So we type our COUNTIF, we select the data, comma, quotes have to come next, and we're going to type that number instead of pointing to it because it's a little easier. So how many numbers are less than 3,903.6? Close the quote, close the parenthesis. Order of operations is important. And computer says, hey, there's 91 of them. Oh, cool. I knew that. But the nice thing is I can just do that over and over again. So here I'm going to count the numbers that are below 1 standard deviation. COUNTIF. Select your data. In this case, it is safe to click on the column heading and get the whole column. Sometimes you have to select the individual numbers. Okay, so here the quotes is required, otherwise it gets messed up. Notice they give me an example saying, hey, put that in quotes. Less than, and I'm just going to retype that number, 2690.9. Close the quote, close the parentheses, enter. So there are 15 numbers below 1 standard deviation. There's 15 numbers below 1 standard deviation below. That's a tongue twister. And there's 91 from 1 standard deviation above and down. So in between, there must be 1591. So I'm going to do a next count between. So this, let's see, count, or let's call it count within, because that's the language it's usually used in statistics. And this right here, column, let's give it a better name. That's now count below. So the count of numbers below 1 standard deviation above is 91. The count below 1 standard deviation below is 15. So the count within would be this number minus that number. So that means there are 76 numbers in between this marker and that marker, 1 standard deviation above and 1 standard deviation below. So I'm going to make a note here. 76 of the numbers are within 1 STD. And we'll do that again for 2 and so on. So you may have noticed there were 2 different commands you could use. The first command is relatively easy, quote, and then put your condition inside the quote where you type the actual number. If you want to refer to the cell that the number lives in, it's pretty complicated, a bit more than that at least. You have to put the inequality in quotes and then say, and look in this cell for the number to check by. So I'm going to try it that way just for fun. So one option would be for 2 standard deviations above, what lies below that, count if, and data, there we go, comma. So the way I did it before was I just did a quote, so less than, and I typed the number I saw, 4509.9. But if I mess that up, right, retyping it, I often mistype stuff. I could have a mistake. So the computer says there's 98. The alternative way to do that, if you want to just grab the number that's in that cell, is you have to close the quote after the inequality, then say, and, like, connect this to that number right there in that cell, and then close the parentheses and hit enter. And it says 98. Repeat that here. How many numbers are below 2 standard deviations below? How many weights are below that weight? And that's a count if. Could you just count this manually by hand? Sure, you can look at these numbers in your standard deviation section and compare them to the numbers in the list when they're ranked, and you can count this by hand. Go for it. It's not too big. Have to use a spreadsheet to do this. Quotes less than, close quote, and compared to that number right there, there are 3 below. So within 2 standard deviations would be this 98 minus those 3, or 95 of them are within 2 standard deviations. And we always want to label things we put in here, so when we look at it later, we know what the hell we were doing. Last one, count if this data is less than this number. All of them are less. Remember, there are 100 numbers here. Okay. And this one, data, comma, condition, in quotes. And you could type the number if you wanted, 1478.1, or you could use that fancy and trick I used a minute ago. They both work fine. All right, 2. So then within 2, there'll be 98 of them, 3 standard deviations, excuse me. So equals this count minus the low count gives me the number in between. 98 of them are within 2 standard deviations. Okay. STDs. So these are the counts of numbers within. Often I have to change the count to a percentage by dividing by the sample size. So I'm going to put that over here, equals this number divided by the sample size. I'd like to fill that down, so the 76 will turn into a 95, but I don't want the 100 to shift down there. So I'm going to adjust this with an absolute reference using, so the numerator is going to change, but the denominators should be fixed. So I'm going to put dollar signs in front of each column and row reference there. And then I can safely fill it down and change it to percentages. Now you might add, oops, wrong button, %. So you might ask, well, why did you do that? Because aren't those right here? Well, it's just a coincidence that I chose a sample size of 100. The sample size is usually something else, 35, 72, 1,115. So we want to change these counts into percentages by dividing by the sample size. All right, almost done. Last thing we want to do, check for outliers. But before we do that, we're going to check out Chebyshev's rule and the empirical rule, and that 5% rule I talked about before. So let's see, 2.7 in our book talks about standard deviation. Standard deviation is a measure of average spread from the mean. At the bottom of this page, they talk about some general rules. And so let's blow this sucker up. All right, so Chebyshev's rule says that, so here's Chebyshev. For any data set, no matter what the distribution is, that means no matter what the shape of the histogram, what we should find is that at least 75% of the data is within 2 standard deviations. How did we fit with that? Well, we found that within 2, 95% of our data was within 2. Is 95 at least 75? Yes, it is. Chebyshev says at least 89%, so 89% or more of the data should be within 3 standard deviations. Did we satisfy that guideline? Yeah, we had more than 89, we had 98%. So pretty much every data set will fit Chebyshev's. Now, Chebyshev, notice, does not reference, oops, where'd he go? Does not he references 2, 3, or more. This one's a little weird. 95% of the data is within 4.5 standard deviations of the mean. And he has a rule for how to calculate this, which percentage goes with which z-score. And by the way, these, the 2, 3, 4.5, those are called z-scores. There are a number of standard deviations. Chebyshev's rule basically says at least none of the data will be within 1 standard deviation. And it is possible that you can have a data set where there is no data within 1 standard deviation. And let me see, can I demonstrate that here? I'm going to try. My drawing tools aren't working, but suppose we had data that looked like this. And I were to graph this data with a histogram, I get what I would call a kind of a U-shaped distribution. So I have a whole bunch of data here and a whole bunch of data there. The mean is going to be right here in the middle, and a standard deviation might be the distance from here to here. So I have none of the data within 1 standard deviation. It could be I even have, let's see, within 2 standard deviations, we should end up out here. So let's just calculate the standard deviation here for fun, just to check Chebyshev out. So we want the mean, wrong order, there we go, and the STD, average data, 6.4, right in the middle here, or a little over because of that taller stack. And the STD in this case equals STDEV data 4.5. So let's see, 6.4 plus 4.5. Oh, that takes me out to 10 there. I guess I'm going to get some in there. So let's see, what is X bar plus 1S? 10.9. Oh, looks like we're going to get all of it. I lied with this data set. All right, looks like I'm going to have to work harder to find a data set that might have less than 50% or so in the middle. But I might get lucky here. What is the mean minus a standard deviation? Oh, check it out. Yeah, so that didn't come close to this stack right here. So in this case, within 1 standard deviation, I'm just going to get the 10s, but not the 1s. And if we take a look at that percentage, so how many data items did I put in here? I put in count 20, and I had some 10s, 12 of them. So 12 out of 20 would be 6 out of 10. So what I've got here is 60% of my data lives within 1 standard deviation. And again, that's going to be all over the place. Before I said usually you'll find a majority of the data is within 1 standard deviation. And for most data, that's going to be true. But sometimes weird stuff happens. All right, so sheet 5 is just me playing around. Play. All right, back to my random sample here. All right, other thing to consider is the normal distribution, which is what this second group is talking about. And Chebyshev's rule says at least 75% of the data is within 2 standard deviations. The empirical rule here says that within 2 standard deviations, approximately 95%. That's a totally different statement. So here, 75% or more should be within 2 standard deviations. Here it says approximately 95%. So that means like maybe 94, 95, or 96%, but not anything else. This says approximately 68%. So that could be 67, 68, 69 maybe, but not 75% within 1 standard deviation. So if your distribution has a symmetric bell shape to it, and it's not skewed, and you find there's 68% within 1 standard deviation, 95% within 2 standard deviations, and 99% within 3 standard deviations, then maybe your sample or your population fits what we call a normal distribution. Maybe it doesn't. Maybe we just got lucky. If it doesn't meet those, does that mean it's not normal? No, it doesn't mean that either. This is just evidence toward saying, hey, this population looks normal. look at all these normal looking samples, or maybe this population isn't normal. Again, maybe, because look at all of these non-normal sample distributions. You just never know. But normal is a powerful idea in statistics, and we're going to use it for some other things. All right, last idea, unusual. So I mentioned before that sometimes we say unusual is out this 5% fringe area. 95% of the data is what we usually come into contact with. So that kind of falls in line with this second line of the empirical rule that says 95% of the data is within 2 standard deviations. So that means there'd be 2.5% out to the left and 2.5% out to the right. So sometimes we use a 2 standard deviation marker to talk about what's usual and what's unusual. So for my data here, if I go with that 2 standard deviation rule, I would be looking at these numbers right here. Now let's make those a little prettier. And this one right here. So I would say I would expect a healthy birth weight to be somewhere between 2,000 grams and 4,500 grams. If a baby is born beyond that, well, that's unusually large for a baby, which is dangerous for the mother, or unusually low birth weight for the baby, which is dangerous for the baby to be born too small. That means it might not be fully developed. And if you think about it, the skewness of my charts here kind of makes sense in terms of it's kind of the mother has physical constraints on how big that baby can get in her belly. So we're not going to see too many unusually large babies. On the other hand, there are lots of reasons babies are born prematurely. And so we will see more often some lower birth weights. It's unusual to have a premature baby. Most babies are born in this kind of natural region, but sometimes we get a few premature ones, but rarely do we get babies that are too big, given the constraints that the baby is growing inside the mother. That's at least my take on why this distribution looks like it does. We could look back at all of the data I have. So the original one had 1,100 data points. So if we look at the graph of all 1,100 birth weights from this study, then we can see that, yeah, there's quite the tail here on the low end. Are there a lot of babies born below 2,000 grams? No, there's not a lot compared to the rest of the sample. Are there a lot born above 4,500? Let's see if 4,500 is about right here. No, there aren't much born beyond that. So just something to think about. All right, that's it for this lab. Hopefully you found this video helpful and your knowledge and skills with statistics are increasing. Take care, do good math. I'll see you in the future. Maybe, hopefully. I'm trying to say goodbye here. Oh, there we go. Hello, goodbye.